something. Oh, I
Does it
think,
work?
yeah, yes, is it?
Okay. So
Let's see, and maybe you may want to do something like a full screen.
yes, just a second.
Yep.
Mhm. Sign up, full screen. Let's see.
Yeah, what to do?
Does it work better like that? Or
I think this is okay. It's probably not the best one,
maybe
but I
to
think we can say it.
let me do it. Let me just so I
Usually
display
some slide mode or something. I'm not
full
quite
screen
sure.
mode. Let's see.
Oh yeah, great. Did it.
Okay.
Okay. So next speaker is yeah, Bonanno. Yes. Um, no, please take it over. I will tell you like after 45 minutes. I will tell you 5 minutes more to go because
Okay.
you
Thank you very
probably needing
much.
10 minutes. Yeah, 10 minutes of question time.
Yes.
Okay.
Thank you very much.
Yep. Go ahead.
Probably. Thank you very much for your invitation and it's really interesting for me to talk about this topic today. And I'll be discussing a work I've been doing recently with Amir Khosravi and Franz Auresig, which is published in Physics Review D recently and also in the archive. The title of my talk is Eschatology of a Regular Black Hole. So I'll be say something about the gravitational collapse and the regular black hole, and also we'll be discussing the Cauchy horizon instability and the mass inflation. And I will study the issue of stability of black hole core. So, what is the problem of? I'm really interested to discuss with you. The problem is the following: the occurrence of singularities in general relativities, as everybody knows, is often taken as an indicator that general GR is an incomplete theory and therefore should be generalized to a quantum theory, which basically spells this feature. Regular, for these reasons, some people have developed the idea of regular black hole geometries. Those are ad hoc modification of general relativity which basically respect the idea, employ the idea of the limiting curvature hypothesis, which I think was first discussed by the Russians, the Russian group by Zeldovich and Zakharov in the late 60s. The idea is that the black hole singularity is replaced by regular piece of the Sitter space. And this is a very interesting idea, of course, but it does come, it comes with some price that you have to pay. Of course, there is no ultimate free lunch, as everybody knows. Typically, the price that we have to pay is that this idea comes with two space-time horizons. We have an outer event horizon and also an inner Cauchy horizon. For this reason, uh, the issue is that global hyperbolicity is hampered by the presence of a quantum, let's say, generated Cauchy horizon. And the question is this Cauchy horizon stable? Because if it is stable, then we resolve this partial singularity in R equals 0, but then we lose global hyperbolicity. So the theory is no longer causal. So if we have, let's say, if we decide that we have the, we set the initial condition in a Cauchy surface, at some point we lose the unicity, unique a possibility of having a unique evolution of our initial data. And this is, for instance, one of the, let's say, implementation of the limiting curvature hypothesis by Sakharov, and this is actually taken from a work by Frolov, Markov, Mukhanov in 1989, which was also implemented by Irina Dibnikova in 1992 with a slightly different model. But the basic idea, as you can see, is the following. We have a global spatial black hole, and in the interior, the R equal constant are actually um, this space-like hypersurface and some hypersurface where the curvature is large enough. We match the spatial interior with the Sitter interior, and that is what you can see. And actually, this H minus ds is the eco-shear horizon for Scri plus in the in our space-time. This, of course, has a deep consequence, because what is the meaning of eco-shear horizon? If we consider horizon nostrum, and the horizon nostrum does have eco-shear horizon inside, and what happens is that this inner surface is actually a surface of infinite plus shift. That means that if an observer crosses the Cauchy horizon, will be causally connected with all the events in the future history of our universe. That is, of course, rather pathological, and therefore Roger Penrose was the first one who said, would basically conjecture that usually those type of horizon should not appear in a realistic black holes. So there has been lots of discussion on the stability of the Cauchy horizon already at the classical level. And let's say the most important work have been the work by Eric Poisson in Israel, 1989, and also Amos Ori, and then other people, among people of myself, have continued this discussion in the early and late 90s. So let's discuss, let's review what happens in a realistic, in a collapse, gravitational collapse of a realistic star, at least, let's say, in spherical symmetry. But the physics should be also similar for Kerr. So in this Penrose diagram that you are seeing on the right, you see the star collapsing inside a black hole, and in the interior part you have you clearly see the potential barrier produced by the curvature, space-time curvature. Now, the role of this potential barrier is quite important, because the outflux of the gravitational waves, which are basically backscattered inside a black hole, this flux that you can see here from this side, it is partially transmitted from the through the potential barrier, and also partially reflected. And the reflected flux is basically here discussed, indicated with its outflux. And in terms of the Eddington advanced time coordinate, we know precisely, because of the no-here theorem and because of analytical and numerical computation, we know precisely in the optical geometric limit how this influx has to decay. It decays as an inverse power law of the outgoing flux. But that's only near this, let's say, singular point in the conformal diagram, which is the point H. If you want to focus on this point H, we should remember this is actually an infinite cylinder. Uh, oh, let's see. Okay, the other there was a. I mean, this is actually an infinite cylinder which extends indefinitely in the past. So what is the outline of the investigation of Poisson and Israel and other people? They basically took into account of the back reaction here of the gravitational waves crossing the Cauchy horizon, and it turns out that the Weyl curvature is singular there, and this singularity is rather strong. Actually, uh, all the curvature invariants near the Cauchy horizon uh, are diverging also in not only in spherical symmetry, and in particular the Coulomb component of the Weyl curvature, which is psi2, and in these complex tethered formalisms, diverges as one of p v to the minus p e to the k minus p, where k is the surface gravity of the inner Cauchy horizon. And because of this exponential growth of the mass function, people have discussed this, have dubbed this phenomenon as mass inflation. And it is interesting to discuss the possibility of constructing exact mass inflation solution to study the instability of the Cauchy horizon. And the rather simple way of doing that is to uh, assume spherical symmetry, of course, and use the 2 plus 2 null formula. So you basically write the metric tensor in as a GABD, say this P where AB are coordinate on the two space orthogonal to the sphere, and you introduce the generalized mass function as the basically the value of the scalar product of the R equal constant hypersurface. This is basically the Misner mass. It is a measure, quasi-local measure of the energy encoded in a sphere of radius R. And over the years, many models of regular black holes have been proposed to mimic the presence of a Sitter interior. Probably the most important one, most famous one, is the Ivar model. And the Ivar model was proposed during at the end of the 90s. And the idea is the following, that the mass function for small r develops the Sitter core because it goes like r to the cube. And for instance, if you suppose that you have a modification of the partial mass given by equation 3, then it's clear that when r is when r is small, you basically have a sort of the Sitter core developing in your system. And here you have only one parameter, this small l is a free parameter. The people think that its value should be basically fixed by an underlying quantum gravity theory. And that's not the only place where regular black holes have occurred. Actually, before the work by Howard, myself and Martin Reuter have developed a similar idea, studying the running of the Newton constant due to quantum gravity effect near the non-Gaussian fixed point, according the asymptotically safe approach to gravity. for which you basically have that dimensionful Newton constant behaves as in equation 4, where omega is a quantity which one can in principle compute. Is of the order of unity, and k naught is a reference scale, an inference reference scale, and k is a momentum scale. So as you can see from equation 4, when k is goes to infinity, then actually the Newton constant is going to 0. That's why it's called asymptotically safe. In this case, what you can do in spherical symmetry, you can relate this k as the inverse of a proper distance from the singularity of a radial geodesic, and after some calculation, you end up with an effective Newton constant, which runs in this way, as in equation 5. And this has dramatic consequences, of course, because at very large distances, you have a very mild modification of the Newton constant, but for small distances, Newton constant goes like r to the cube. And again, this will lead you to a sort of a sorry, de Sitter core. And in fact, the causal structure of the singularity is similar to the Reitzner nostrum, except from the fact that r equals 0 is now time-like, but is not singular. And you can see here that you do have a Cauchy horizon in the interior, which then the question of stability occurs again. Is this a reasonable causal structure for, let's say, effective quantum gravity generated black hole, or this is something which is still too far from reality? So what we did in this work, which was the following: we tried to construct an explicit solution of a regular black hole, which should be basically should arise in a realistic collapse. And you can see here, what we had in mind is something similar to the previous conformal structure here. The difference from with this potential barrier here with this conformal structure is that here we are basically modeling the outflux of the outgoing star of the end of the backscatter reaction with a single shell. So what we did here, we used an idea by a model which was in the 90s was constructed by Amos Ori for studying the mass inflation model, which consists of joining two in that case were two Reisner Nostrum black holes, but here we have two regular black holes, which are basically which describe the two space-time M plus and M minus, and we match these two geometries along an outgoing null shell, which is sigma. And then what we do, as a boundary condition, we consider the presence of ingoing flux of radiation due to the outer potential barrier. So we basically have a cross-flow region where we have both the outflow and inflow considered. And in this case, to be more precise, what we did exactly is to assume that we have these two Bahia type of geometries described in equation 8. The plus minus refers to the future sector of the shell. the minus sign refers to the pass sector of the shell, and we generally have two different mass functions. We want to consider this system, match these two geometries across the shell, and predict what is the outcome of the mass function behavior in the future sector of the shell. So that's possible to do that with the formalism which was developed by Israel and Barrabes, and basically what you do, you have to be sure that the induced metric on sigma is such that the r coordinate is the same on both sides. And to do the actual calculation, it is convenient to choose r as a parameter, not necessarily a fine, along the null generators of the shell, and assume that on both sides of the shell you have the Einstein equations valid, of course, which are in this case given by equation 9. So when you do that, then you want to have you want to assume the continuity of the flux across sigma, and where here in equation 10 the bracket, the square bracket, means a jump across the shell. And if you basically develop this condition, you will end up in equation 11. Equation 11 is basically an equation which relates the mass function on the future sector of the shell with the mass function on the minus sector of shell. Yes, are there questions? No. So the functional dependence of the geometry is also fixed by noting the position of the null hypersurface must satisfy equation 12, of course, along sigma. And basically, this set of equation will has to be satisfied along the outgoing null shell. So for these reasons, what happens that you basically, we choose the Hubbard model. So we specify the lapse function as in equation 13. And because the shell moves light-like, we also had to assume the light-like outgoing geodesic equation, which is equation 14. Equation 14 is actually the equation for the shell, which is the same and must be solved once for both sides of the shell. Then you have the continuity equation, that I've just shown you, and that is given by equation 15. So basically, equation 14 and equation 15 is a system of two first-order differential equation, which you can only solve in the limit of v going to infinity. And the reason why you can do that only in this limit is because everything we are doing, it only holds in the optical geometric limit. In fact, the boundary condition, the event horizon, is determined by the price-tail behavior. And the price-tail behavior is told us is represented by equation 16, which is only valid in the limit of v going to infinity. It's the optical geometric limit. In this limit, the ingoing flux, which is penetrating the black hole, is represented by this function, and P is 2 times 4L plus 1 for a multiple of our order L. Now, if you do that with some asymptotic analysis, you can use the Frobenius method. You can easily show that after some algebra, M plus behaves like equation 17. So M plus actually goes to a constant at the Cauchy horizon. This constant makes this behavior has a tremendous impact in the discussion in the curvature, because the Crashman scalar, the Kretschmann curvature is singular at the Cauchy horizon. Now, this figure that you see here comes from numerically solving the evolution equation, which I've shown you for the mass function in for the original Israel-Poisson model and this new regular Poisson model. You can see that as v increases, and this is in a log-log scale, m plus goes to behaves like a power law in the case of the regular black hole, while in the previous original Poisson-Israel model, you had basically a power law behavior. This is actually is a log-log scale, even though it's not written in the labels. Therefore, this line, the orange line, is exponential, and the blue line is actually power law. Now, this has a very important consequence, because let's look at the strength of the singularity in the original Poisson-Israel model. Now, in the original Poisson-Israel model, if we indicate with V plus the advanced coordinate in the future sector of the shell, a large values of V plus, the metric near the Cauchy horizon. Remember, the curvature was singular, but the metric can be written in this simple way, equation 18. And you can justify a new coordinate u in this way and obtain a metric like in equation 20, which is completely regular at the Cauchy horizon. So this is something very special, because it is clear we are near to a whimper type of singularity, where even though some curvature invariant of the metric are singular, the metric itself is regular at the Cauchy horizon. So some people have actually speculated the possibility of crossing the Cauchy horizon. And so what happens here? The singularity is already in the classical case is, as I said, rather weak, because it is possible to find a coordinate system where the metric is regular. Actually, it is possible to show that the mass inflation singularity does not satisfy the necessary conditions to be strong in the Tipler sense. And null singularity is said to be strong according to Tipler if there exists at least one component of the Riemann tensor that in a parallelly propagated frames, the twice integration with respect to the affine parameter tau does not converge. So this physical meaning of this requirement is that the tidal distortion is not finite as an observer crosses a strong scalar singularity. A measure of the latter quantity can be obtained by twice integrating the tidal acceleration as provided by the square of the wide curvature. And actually, if you do so for the original mass inflation scenario, the square of the Weil tensor behaves in this way, according to this law, as v goes to 0. Where v actually is really the crucial coordinate adapted to the inner horizon, which is proportional to the proper time of the observer in this case. And therefore, if I do twice integration of that, actually this is finite. And Amos was the first one to argue that this behavior could be sufficient to determine a C1 extension of spacetime along the Cauchy horizon. However, according to Krolak, 21 is still a strong singularity as the expansion of the congruence, the null congruence across the Cauchy horizon is divergent. In fact, in this case, if we integrate the Riemann-Christoffel tensor only once, the integral does not converge on the singularity. But what happens in the case of a regular black hole, what we just saw, because of this power law singularity? Now the square of the Weil tensor behaves as log minus v 3p. P goes to 0 from a negative, from negative values. And this function is that even though it's directly integrable. Therefore, at variance with the original Poisson-Israel model, the singularity produced at the Cauchy horizon in regular black hole is Krolak weak. So therefore, not only the volume, the congruence, T is Tipler weak, but also the expansion does not diverge negatively at the Cauchy horizon. And therefore, this is a strong, very strong further evidence which supports the possibility of the C1 or maybe even the C2 extension of the space-time beyond the singularity for this type of regular black holes. Now, of course, this is in a sense, this is a problem. Why this is a problem? Because the conclusion that we are reaching are basically the following. The regular black holes in spherical symmetry have Krolak weak singularities, okay? And so the space-time, in a sense, can be extended beyond the singularity. And the question is the extension unique? We have this result that we can cross the singularity, we can cross the Cauchy horizon is still unstable, we can cross the Cauchy horizon, and we basically have a C1, C2 extension of space-time, but this extension is most probably not unique. And the reason is that because the global structure of the space-time loses global hyperbolicity. So basically what we are saying is that if this model is correct, if regular black holes are a good, let's say, are what we expect to happen as a consequence of quantum gravity effect near the black hole singularities. What is happening here is that we are losing the possibility of having a unique evolution of the initial data in all the space-time. So it is something, let's say, still problematic, because we would like to have a theory of quantum gravity where this does not happen. So what to conclude about that? I have a personal opinion that we need to specify, to better specify the actually the continuity equation in a sense that we have to give we have to have a physical model for the evolution outside the Cauchy horizon. This is not something strange in physics, because if I can make an analogy, what is happening here is something similar to the development of a shock in fluid dynamics. When a shock develops in fluid dynamics, like in the Navier-Stokes equation, we are confronting with the fact that we lose the possibility of extending the initial data. In that case, what we do, we use the Rankine-Hugoniot matching condition, which are basically a consequence of the fact that the entropy must increase across the shock. So we have a way of selecting a unique evolution using a physical requirement. And we probably have to do the same if we believe that these models are correct. Of course, one can imagine that this is clearly a very, let's say, very limited model of black hole interior, because there are two important ingredients which have not been taken into account. The first one is the back reaction of the Hawking radiation. near the in the Cauchy horizon. The Hawking radiation provides a negative influx of energy, which actually decays much slower than the price tail, and can change completely the structure of the singularity there. And the other question is the fact that all these models basically assume that the Cauchy horizon exists. So all these calculation by Ori, the first calculation by Poisson in Israel, actually have assumed that the Cauchy horizon is there, and they study the stability. But what will be really much more, I think, urgent to do is to remove the assumption that Cauchy horizon is there, and actually, and follow the full evolution of the space-time up to the development of the inner singularity, whether a singularity is there or not. This is a work which has not been done, and I hope in the future that me and my colleagues will be able to address. So I think that is the only thing of which I have to say for today, and I think I finish a few minutes before. So if you have questions, I'll be happy to take your questions and try to answer your question. Thank you very much for listening to me and to this talk.
Okay, thank you. Any questions? No? Okay. Just one thing. I think probably this is what you said at the end. Um, end means, yeah, this conclusion. So if we put any perturbation, does all these structure of the Cauchy horizon and so on stays? That was something I was wondering throughout the talk. But probably you said it has to be done and not yet done. Like
Yes,
realistic, any perturbation and so on, and right,
yes, this is
dynamically
only
follow it.
that's right.
Yeah,
What one has to do is really to not assume that the Cauchy horizon and to
yeah.
follow the full solve the constraint equation and the Einstein equation, including the Hawking radiation provided by this regular black hole. And this is difficult to do because numerically you have to look at in this region, sorry, here, in this corner region, where you basically map in a finite distance of conformal time, an infinite distance in the advanced time. So it's not so obvious how to do that. Some people have done, because you see, even a small finite distance here is an infinite distance in terms of the advanced time. So therefore, you need proper treatment of the numerics so that you are sure that in this limit you get a solution which is convergent to the real solution. And that's not so obvious, but some people have done that. And in principle, I am confident that at least in 2D, in spherical, let's say, in spherical symmetry, it should be able, one should be able to have a precise answer, because the question is simple. You just have to solve the say the evolution of the collapse up to the development of the Cauchy horizon, and you have to change the boundary condition, including not only the price law but also the let's say the Hawking radiation. So in principle, one can do that. There are some codes available in the literature, and I'm confident that in the next few months we should be able to start to address this question in a consistent way.
Sounds great.
Thank you very much.
Is there any other question? Okay, if not, let's thank Alfio again.
Thank you very much.
Okay.
Thank you very much. Thank you very much for this very brief talk. Okay, I stop sharing now.
Yep. Okay.